Hi, in today's video, we'll continue our exploration of simple linear regression. So remember that in a linear regression, we have our dependent variable, yi, which is equal to alpha plus beta times xi, our independent variable, plus ui, our error term. Now, several assumptions are needed for the OLS estimates to be the best possible. Okay, technically, we would call that the best linear unbiased estimator, where unbiasedness is a property that we want for our estimators. So what do we need basically for the OLS estimator to be a good estimate? Well, first of all, we need the model to be linear in parameters. That means that here, when we make these assumptions of linearity, it's actually correct. In expectation, the error term needs to be equal to 0. And the variance of the error term does not change depending on the observations. Moreover, we need to make sure that the error term is normally distributed and ui is distributed independently of uj for all j different from I. So a lot of those assumptions are a bit technical. So for example, this assumption basically means that the error term for observation I is distributed independently from the error term for observation j. So the two error terms are not related to one another in any way. But the most important assumption is the last one, that ui is distributed independently of xj for all j. Okay, so here what this means is that there cannot be a relationship between your error term and your regressor for you to be able to recover estimates that are basically good estimates. If xi and ui, for example, are correlated, or if there's any relationship between them, that would cause a real issue down the line. So this is the assumption that we'll be most concerned with, and we'll see in future videos that this will cause all kinds of problems. So we need to find a way of modeling our outcome variable, yi, in such a way that our error term is uncorrelated with any regressor. Now, if we have this, then we will be able to have, for example, unbiased estimator. Now, the solution that we'll get from ordinary least squares, so by minimizing the sum of squared residuals, is as follows. So we get b is equal to the sum from I is equal to 1 to n of xi minus x bar times yi minus y bar, where x bar is the sample mean of x and y bar is the sample mean of y, divided by the sum from I is equal to 1 of xi minus x bar, the whole thing squared. So that is for b. For a, we simply get y bar minus b times x bar. Now, one thing that you can notice with our estimator b is that the numerator looks very much like the sample covariance. If I just added 1 over n minus 1 in front of that term, I would get the sample covariance. And similarly, if I put 1 over n minus 1 in front of my denominator, I would get the variance of x. So here we can see that we basically have the sample covariance between x and y divided by the sample variance of x. So another way in which we can express our estimator b is as the sample covariance between x and y divided by the sample variance of x, which is related to the correlation, but it's not exactly the correlation. It's the correlation between x and y times the standard deviation of y divided by the standard deviation of x. And this is actually relatively easy to prove because the correlation between x and y is equal to the covariance between x and y divided by the standard deviation of x times the standard deviation of y. So if I do times standard deviation of y over standard deviation of x, I can see that different terms cancel out. In particular, the standard deviation of y cancels out with the standard deviation of y in the denominator, and the standard deviation of x times the standard deviation of x is just the squared of the standard deviation, which is equal to the variance of x. So I get back my formula, which is the covariance between x and y divided by the sample variance of x, which is what I had for my estimator B. Okay, so this is a formula you can learn as it's quite helpful to understand the relationship between the correlation and the estimator for the OLS slope. So graphically, A corresponds to the intercept, which is the predicted value of y when x is equal to 0. And one thing that I would recommend you to do is actually learn that sentence by heart, okay? Because you'll very often have to interpret your estimates, and knowing a sentence by heart like this one will mean that you will never make a mistake. So in this case, the intercept is the predicted value of y when x is equal to 0. Now, you cannot always interpret the intercept in a meaningful way. So in this example, my intercept is equal to minus 138, which would imply that a person who is 0 centimeters tall is minus 138 pounds. Remember that we were looking at a model linking height to weight. Now, the reason why this estimate doesn't make sense is that we're looking at values for x that are so far from the values of x that the predictions are pretty much nonsensical. So in this case, we know that in terms of height, if we think about centimeters, will be between maybe 130 and 190. And it doesn't really make sense to look at heights that are extremely small, and especially a height of 0 makes literally no sense. So the fact that you cannot interpret the intercept in a meaningful way does not mean that the model is wrong. In this case, for example, the linear modeling seemed to be relatively good. It's just you can't extrapolate it very far from the values of x that are actually the values of x you observe in your sample. Now, for B, we just say that B is the slope of the fitted line. So in a particular example, B is equal to 1.66, and that means that a 1 unit increase in height in my x variable is associated with a 1.66 unit increase in weight, my y variable. Okay, and that's also a sentence I would learn by heart. So the 1 unit increase in x is associated with a B unit change in y. And I say change here because if B is positive, it's going to be an increase, but if B was negative, then it would be a decrease. So if we look at the equation for the fitted line, we get that my predicted value for weight hat, is equal to minus 138.82 plus 1.66 times height, and minus 138 is my estimate for the true parameter alpha, and 1.6 is our estimate for the true parameter beta, okay? And so now if I wanted to get a predicted weight, I could just put any height in centimeter, let's say 150, and then I would get the predicted weight by doing 150 times 1.66 minus 138, and that would give me my predicted weight based on the sample that I got. So that's it for today's video, and I'll see you on the next one.